Hi friends, welcome to GMK tutorials. Still if you are not subscribing our channel, so please subscribe our channel for latest videos. So today we are going to focusing on one of the important topic in sharpening of a spatial filters. So it is related to image processing subject. Okay, under the image processing concepts, spatial transformations, or we can also call it the spatial transformation operation point of view. Okay, sharpening of a spatial filters. So let us see. So the principal objective of sharpening is to highlight a transitions of a intensity. That means, is there any changes in the intensity values that can be highlighted with the help of a sharpening? That is one of the most important. As well as image blurring could be accomplished in the spatial domain by pixel averaging in the neighborhood. Suppose if you want to blur the image, that can be accomplished by using a spatial domain pixel averaging. That means if you are taking some neighborhood of information, within the neighborhood a 3x3 matrix is there, all values are added. By dividing the all values with the total number of pixels, you can get the average value. So if you are replacing the corresponding average value with the central pixel in the corresponding original image, the image is blurred. That is nothing but image blurring operation, right? So that is nothing but image blurring. So because of the averaging, what happens is that sharpening can be accomplished by spatial differentiation. So sharpening can be accomplished by using a spatial differentiation. So with the help of a differentiation operation, we can identify the corresponding sharpening filters. As well as the strength of the response of the derivative operator is the strength of the response of the derivative. The strength of the response of the derivative operator is proportional to the degree of intensity discontinuity of the image. That means the strength of the derivative operator. The strength of the derivative operator is directly proportional to the intensity changes in the discontinuity. Intensity discontinuity of that image. That means wherever the transitions from object to background or background to object transitions are there, at that time it easily identify the corresponding strength is maximum value at that point. So based on that concept, we can identify the edges in the images also. That is one of the basic principles. As well as image differentiation enhances the edges and other discontinuities. So with the help of a differentiation operation, we can enhance the edges as well as other discontinuities and de-emphasize the areas with a slowly varying index. Wherever this slow changes in the intensity values, that can be de-emphasized. That means we can suppress the corresponding values. Okay. So as well as the derivative of the digital function are defined in terms of differences. Basically, the differentiation is the differential equations for continuous domain. But if you go for the digital images concept, the differentiation means the difference of their values actually. So in case of the differentiation, we have two types of differentiations: first derivative and second derivative. So these are very important. Based on this one, we can use so the first derivative having some important points, that is must be, that means the first derivative must be 0 in the areas of constant intensity. Wherever the constant intensity is there, at that time, if you are finding the derivative of the corresponding constant intensity, that value must be 0. That is the point number 1. Second point states that it must be non-zero at of intensity transition. Suppose is there any intensity transitions like this, or maybe step transition, at these two cases the derivative is non-zero. So that is a for first derivative concept. But if you go for the second derivative concept also, second derivative, it must be non-zero at a constant intensity, similar to first derivative point, as well as so in case of the first derivative, that value is equal 0 for constant intensity. In case of the second derivative, what happens is that must be non-zero. That means the value may be non-zero for the constant intensity in case of the second derivative. At the same time, second point means must be non-zero at a constant onset and end of the intensity ramp. So as well as is there any changes in the edges, maybe ramp like structures, at that time that value is also must be non-zero. As well as third case is nothing but must be 0 along the ramps of a constant shape. Is there any ramp like structures like this? That value must be 0 in case of the second derivative. These are the some of the important observations in case of the first derivative and second derivatives. Okay, let's move on to the next slide. So in case of the first derivative, these are the formulas for first derivative. F of x is the difference. So dou f by x is the first derivative, that is equal to f of x plus 1 minus f of x. As well as second derivative can be represented like this, f of x plus 1 plus f of x minus 1 minus 2x. So as well as edges in the digital image is often ramp-like transitions. So therefore, the first derivative of the image would be result in a thick edges because the derivative is a non-zero. So that means wherever the edge transitions are there, with the help of a first derivative, we can highlight the corresponding areas. As well as the second derivative would produce a double edges 1 pixel thick separated by zeros. So the second derivative enhances the fine details much better than the first derivative. So apart from that, there are the other filters also there, that is nothing but isotropic filter, whose response is independent of direction of the discontinuities in the image to which filter is applied. So isotropic filter means the name itself, isotropic means it is a constant value. So wherever the isotropic filter whose response is independent of the direction of the discontinuity, whatever the direction of the discontinuity, that value must be maintains a constant, like it may be independent on the direction of the corresponding edges also. As well as isotropic filters also rotation invariant. Suppose if you are changing the corresponding direction or in a rotational format also, it is also independent. These are the some of the isotropic filters. So the isotropic filters derivatives is isotropic derivative operator is a Laplacian operator. We can also call it a Laplacian operator is the isotropic derivative. So it is nothing but a two-dimensional. Second derivative. Therefore, del square f by del square f by dou x square, dou square f by dou y square. If you are expanding this equation, we can get like this the total equation. Okay. So then the corresponding, these are the different types of filters for Laplacian filters. So for filter mask, for if you are taking the diagonal elements, it is for C, and the other implementation for the Laplacian filters. So it is a quick revision. Actually, these concepts are already covered in our videos also. So because of the Laplacian derivative operator, it highlights the intensity discontinuities in the image. Therefore, it is used for identifying the edges also. So one drawback in case of the Laplacian filter is nothing but it is very sensitive to the noise. So that's why if you want to use the Laplacian parameter, Laplacian filter, first of all you have to smoothen the image, then you can apply the Laplacian parameter. Okay, so that is also one of the So here there is some points related to this one. A background features can be recovered while still preserving the sharpening effect of the Laplacian simply by adding the Laplacian image to the original image. That means if you want to preserve the background information, at that time you have to add the corresponding Laplacian filter to the original image. As well as if the definition used as a negative center coefficient. In case of the filters, we are using a -4 like this, negative filter coefficient. Then we subtract the rather than add the Laplacian image to be sharpened result. So if you are using the negative center coefficient, then we subtract rather than adding. That means if you are using the negative center coefficient, then you have to subtract. If it is a positive, you can add it. So that is some of the observations in case of the Laplacian pyramid. G of x comma is equal to f of x comma by c into del square f of x comma, where f of x is the input image, g of x comma is the output image. These are the known terms. Therefore, where constant C is equal to -1 if the Laplacian parameter A and B, and C is equal 1 if either of the two filters. So that is nothing but Laplacian filters.